Hey guys, Miss Peterson here, and welcome to AP Physics 2, Lecture 3-2, all about the electric fields. We're going to be talking about what electric fields are, how we draw electric fields and represent them using electric field lines and vector field forces. We'll also be talking about isolines. Okay, so what is an electric field? I think one of the easiest ways to think about it is to relate it to something that we're a lot more comfortable with, gravity. Okay. A gravitational field is anywhere around a mass where another mass would feel a gravitational force. And it is the same for electricity. Okay? If you have an electric force, any charge placed in that electric field will experience a force due to that field. Okay? Now, when we draw the electric field lines, they are always pointed away from positive charges and toward negative charges. The way I like to think of this is you're drawing them from the perspective of a positive test charge. So it's the direction that a positive charge would go. Okay, when you have a more dense field lines, that means you have a stronger electric field, like in the middle of these two charges. And note the lines will never overlap. Okay, I highly recommend you see what these look like in the PhET charges and fields simulation. So if we wanted to quantitatively calculate the strength of that electric field, well, it's the force that a charge would experience due to the charge that is creating the field. So its units is the force per unit charge. So newtons per coulomb, force per charge. Okay. So we know the electric field is going to be the strongest closest to the charge. And it will be the weakest farther from the charge. So the equation that we see for this one is in two ways, that the electric field equals the force that the electric experiences divided by Q, okay? So in this equation, this is the electric force, and this is the charge experiencing the field. Okay, now we can look at that a little deeper and do that derivation. So we have that the electric field is that electric force divided by that charge. Because basically when we figure out these forces, we want to get rid of the thing that's experiencing it and just focus on the charge creating the field. Now, if we're doing force, we're talking about two charges. So you can think of that as one of them creating the field and one of them experiencing the field. So one of them cancels out, and we have KQ over R squared. And that is our other equation for the electric field, that the electric field equals K times Q over R squared. Now note when we use this equation, this Q is the source charge. Okay, it is the one creating the field. Okay, so this equation we tend to use more if we're talking about the electric field around a point charge, where if we're talking about the force or something experiencing an electric field, we'll tend to use that top one. Okay, cool. Okay, cool. So let's go ahead and talk about that force. Okay, the main thing that makes electricity more confusing, I guess, than gravity is the fact that negative charges flow uphill. Okay, when we talk about gravity, gravity only pulls things in. Okay, gravity is never going to exert a force on me to make me fly up off my chair right now. It's only going to attract me towards the earth. But for electric fields, while positive charges feel a force in the same direction as the field, Negative charges feel a force in the opposite direction of that electron field. So if we look at this example here, where we have an electric field with a value of 60 newtons per coulomb pointed to the right, and then it asks what is the magnitude and direction of the force on each particle. So for the, we have an electron and a proton. We need to get their charges, okay? We know that. We know the electric field strength is 60 newtons per coulomb. And then the Q proton will be 1.6 times 10 to the negative 19 coulombs. And then Q electron is that same value, but negative 1.6 times 10 to the negative 19 coulombs. Okay, so we're going to be using one of our new equations where the electric field equals that electric force divided by the charge experiencing the field. So in this case, the electron, proton, neutron. We do not have any information about the charge creating this electric field, so we can't use that other equation. But we can use this one and reorganize it so that electric force equals the electric field strength times the charge. So let's go ahead and figure this out. For the force on a proton in the field, we have the electric field strength, 60 newtons per coulomb, times the charge on a proton, 1.6 times 10 to the negative 19 coulombs. Okay, we plug that into our calculator. And we get 9.6 times 10 to the negative 18. The coulombs cancel out, so this will be newtons. Now, it's a positive number. That tells us the direction for a vector, so it'll be right, that same direction as the electric field. Where if we look on the force on an electron, okay, we have the same electric field strength, but now we have negative 1.6 times 10 to the negative 19 coulombs. So our answer is negative, but all that means in this situation is that it is directed to the left. Okay? So there's the proton and the electron, but what about the neutron? Well, the force on the neutron, we have the 60 newtons per coulomb, but neutrons have a charge of 0 coulombs. So we have no force on the neutron. Okay, cool. Okay, cool. Now, let's go ahead and do some vector math and look at the electric field around point charges. So we're going to be using that other equation. Okay, this problem is asking us what the electric field is on point P. And I did something funky here. Let me undo that real quick. There we go. What the electric field is at point P. So it has an electric field contributed from this charge and this charge. Remember, the electric field is in the direction that a positive test charge would feel a force. So let's go ahead and draw in those forces. Okay, a positive test charge would be repelled from point B. Okay, so there's the electric field due to B in that direction, while it would be attracted to that one. So here we have the electric field due to A. And we will be solving for both of these using our equation that the electric field equals KQ over R squared. Okay, where again that R is the distance to the point charge and Q is the charge creating the fields. This prefix right here is micro, and it means times 10 to the negative 6. Okay, so let's go ahead and start solving out this problem. Okay, so we're going to find what is the electric field at point P due to charges A and B. So let's go ahead and start with due to A. So E due to A is going to be KQ over R. So we have 9 times 10 to the ninth Newton meter squared per Coulomb squared times the charge, which is -3 times 10 to the -6 coulombs, divided by R. We need to get this distance here, and we don't have that yet. But it is a triangle. This is at -2 meters, so 2, and this is at 7. So A squared plus B squared equals C squared. 4 plus 49 is 53. So this length would be the square root of 53. I'm going to keep it that way because when we plug it into our electric field equation, it gets squared. So that will undo the square root. Okay, so we plug that all into our calculator. Times 3 times 10 to the -6 divided by 53. And we get 5.0943. Okay, we only have one sig fig on each of those, so I'm just going to round it and say it is about -500 newtons per coulomb. Okay, it's negative because it is in that downward direction or towards that charge, which means if we did E due to B, okay, it would be in the opposite direction, so that would be 500 newtons per coulomb. Okay, but we are not quite done yet. Okay, that is the contribution to the electric field, but we can tell from this diagram that those are not going to be in the same direction. Okay, we have one pointed down and one pointed up. Now, if we look at this, can you tell which components are going to add to make our vector math a little easier? Okay, well, we have one up and one down, and those are going to be equal. So the y components of this force are going to cancel. And the x components will add, okay? Because they're both pointing in the same x direction, but opposite y directions. So let's go ahead and figure out what those x and y components are, okay? So I'm going to set up my components like they were two vectors that added up to that. Let me go ahead and find that angle there. I'm going to find that angle from the, I'm going to find that angle from the inverse tangent of opposite, which is 2/7. Okay, that'll give me that angle. Making sure my calculator is in degrees mode. And I get 15.9, okay? So about 16 degrees. I'll use 15.9 in my math just to make it a little bit more complete, okay? And if I'm looking for the x component of it, if I'm looking for this component of it, that is the opposite, okay, in the way I drew it. So I'm going to use sine, okay? So for the x components, okay, we would have the force in the x direction is equal to that force, the net force, or the hypotenuse, if you will, times the sine of, what was that angle? 15.9. Okay. And we plug that into our calculator, 500 times the sine of 15.9 to get a force of 137 newtons. Okay, so about 140. So then the net force would be 2 times that, okay, which is going to be about 274, okay, about 270 or about 280 newtons per coulomb in the leftward direction, okay? Okay, cool. Okay, cool. Now, if an electron were placed at that point, what would be the direction of the force? Well, if the electric field points to the right, electrons flow uphill. They flow opposite the electric force. So the direction would be to the right. And then to find the magnitude, we would use that the electric force equals that electric field strength times Q. Okay, so we have the electric field strength, which we just found as 280 newtons per coulomb to the left times the charge on an electron, which is the fundamental charge, 1.6 times 10 to the negative 19 coulombs. And you get a force of 4.48, so 4.5 times 10 to the negative 17 newtons to the right. Okay. And again, one of the ways you could have thought of this is because the direction is to the left and that's negative, we could say that's negative, and we would have a negative charge and a negative charge there to make that positive and show that opposite direction. Okay, cool. Okay, cool. So now we're going to talk a little bit about electrical potential energy, okay, which we'll be diving into a lot more in the next lecture. But before we do that, I want to talk about topographical maps, okay? Now, I find it unlikely that you've seen a topographical map anywhere except maybe a video game. But what they do is they show lines of equal heights, okay, of equal heights on the hill. Now, you can think of that equal height as equal gravitational potential energy, okay? So if I was walking along this 20-meter long path at that same height, there would be no change in my gravitational potential energy as I move along that line, okay? Now, if we were doing this for Earth, okay, its isolines, or lines of equal height, would just be the dotted lines around it, okay? Lines of equal height or distance away from the mass creating the field, okay? Now, around the Earth-Moon system, okay, there's our moon, okay? Granted, the Earth has lines of equal height. The moon is a lot smaller, so that line would be a little bit closer to the moon, okay? Or sorry, a little bit farther, okay? Because that has less gravity. This one is a stronger gravitational field, so we would have more of those isolines. And then there's some point around them too that you have this like equal height all around them, okay? Due to that electric field. We do the same thing for electrical potential energy. And we call those isolines, and they are maps of equal voltage, okay? We label them using volts. Now, if these are the electric field lines, the red and the blue, okay? The isolines are the circles going around it, okay? No work is required to move along an isoline, and we measure the units of it in volts, where 1 volt means 1 joule of energy per coulomb of charge. Okay, so it's telling you the energy per charge, similar to the energy per mass of like gravitational fields. Okay, and that is what voltage is. It is a measure of the electrical potential energy per unit charge. Now, high voltage means high potential energy. And we usually, when I'm talking about high potential energy, I mean high in magnitude, okay? Talking about the magnitude there. While here, where we have those negative voltages, that's because we have negative charges creating those fields, okay? So negative charges have negative potentials around them. Potential, aka voltage. Okay. Now, negative charges go uphill. So they will move from lower voltage to higher voltage. Okay. If we had a negative charge in this field, okay, these are showing you the isolines, electric field lines, isolines. If we had a negative charge there, it would be repelled by this negative charge and flow out, flowing towards zero, toward a higher voltage, while positive charges move from high to low, Okay. You can also think of it negative charges going from negative to positive because they're repelled by negative and attracted to positive, and positive as positive to negative. Okay. And we'll dive a lot more into voltage in our next lecture. But that's it for today. Okay, cool. Okay, cool.